Hi everybody, welcome to the first day of school. I've been going to the first day of school all my life, it's kind of crazy. Anyway, we're glad to see you all here for quantum optics. Most of you know me, those of you who don't, I'm Ivan Deutsch. And we will have two TAs helping us this semester who are currently here in the back. They won't be here every day, at least both of them won't be here. You have your name tags, that's great. Do I need one too?
We can make you one.
Manuel Munoz and Anupam Mitra. So, the first thing we need to do to get started today is to talk a little bit about administration. So firstly, let me just first begin by talking a little bit about what is required for this course, at least according to the course catalog, which is the actual prerequisite for this course is Physics 521 and 522, which is the year of graduate quantum mechanics. But I know that some of you in the class have not had that course. It's not essential for this course that you have taken that course. In terms of the facts, that what I want to say is there will be an expectation of good comfort level with quantum mechanics and being able to work easily with the formalism of quantum mechanics. And one has that when one has had a graduate course in quantum mechanics. But if you've had a pretty good course in undergraduate quantum mechanics, that will most likely suffice. Okay? In the sense that we're not going to be using very many advanced topics that are covered, say, the Wigner-Eckart theorem or something like that, which you may never have heard of if you didn't take a graduate course in quantum mechanics. That's not essential. But what is essential is, seriously good comfort levels with dealing with the formalism of quantum mechanics. If you have any questions or concerns about that, you can come talk to me and we can discuss it. Okay. So, most importantly, in order to access all the materials for the course, one needs to be able to access our website. So the website for the class is linked through the department's list of courses. I will email everyone as well, but let me just make sure that you have it, because it's essential that you have that. And everything, I won't be distributing any paper. So all of the homework assignments and any other handouts will be downloadable here on the website. And you'll find all the information about that. Firstly, there is no required textbook, of course. I am particularly idiosyncratic about the way I like things covered. No book ever does it the way I want to do it, so I do it my way, and you're forced to get that perspective. However, that doesn't mean it's the only perspective, and it's important for you to get other perspectives as well and seek out other course materials. And so a whole bunch of textbooks are listed here on the website, and you can take a look at them and see what you might want to have for your library. And I do recommend checking some of these other texts out to have other reference materials. Okay? But I guess I'll come down here first. What that means, though, is that there will be lecture notes that are distributed here on the web, and this is the aspirational syllabus and list of lectures that we hope to cover this semester. And so, for example, oops, what just happened there? If you click here, the first lecture is downloadable, and you can get them. And I will generally upload them just before class, because I want to go through them and start to do a little quality control and correct mistakes that have been accumulating over 15 years and not cleaned up. Umpteen equals 15 or something like that. Right. Okay, let's see, what else to say about the organization of class. So, is it listed here? Oh yeah, here it is. You may be interested in how you get your grade for this course. So, the grading is as follows. There will be homework. The homework will be most weeks. There's something like 15 weeks in the semester, and we'll have 8 to 10 homework assignments. And they'll typically be due in a week. So they'll be distributed on Thursdays and then due the following Thursday, say 5 o'clock in Manuel's mailbox. And we'll talk about office hours and other help for that. There will be one exam. There will be a midterm exam just before fall break. And then there will be a final project as well. Okay, we'll kind of stop homework at some point around, before Thanksgiving, so you guys can have time to work on your final projects. Right. So the list of topics are here, what we will be discussing this semester. Well, I think much of this will be become clearer as the semester unfolds. I guess there's one other general comment I wanted to make, which is beyond the prerequisites. I know that there is we have a very set of students in the class this semester, some of whom come with quite a bit of background in certain topic areas and others not. And we'll do our best to speak to everyone in the classroom as best. But that means for some of you, sometimes, it might go a little too slow, sometimes it might go a little too fast. It's just how it's going to be given the distribution that I know exists in the classroom. Okay. But also, you should absolutely feel free throughout to interrupt me with questions, anything. I want this to be a discussion as much as possible. So while I do have the gift of gab, you should definitely interrupt me as time progresses. Okay. Does anybody have any general questions about the administration of the course? Yeah.
Monday, Labor Day, there's no class.
Right. Yeah. So that's baked in to the schedule. Once in a while, I'm called away and have to travel, and we may have to cancel class and have a makeup. At this point, the only time I know that I'm for sure traveling is the week before fall break in October. And currently, that time is where I've scheduled the exam. Okay, so right now, there's no other travel on the schedule. But Labor Day is here, and there's no class. Any other issues, questions? Right. All right. What's quantum optics about? This was a little crazy flow chart I put together oh God, around 2002 or something, I think the first time I taught this course. And it's surprisingly, I think, still quite relevant. Quantum optics, as I see it, is a fairly broad subject that brings together different streams of development and research that have a commonality to them. Okay? Traditionally, people talk about quantum optics in terms of issues related to the nature of light itself. The quantum mechanical nature of light is what I would say, if you ask people what is the subject of quantum optics, that's what they would say. Quantum optics is about quantum light. But I think the subject is broader than that. It's really the story of quantum mechanics itself. And the subject of quantum optics is the subject of quantum coherence. And we'll come back to this in our introductory discussion today, what we mean by that. And coherence, as I'm putting it, has these two streams, one having to do with optical coherence, and this is the subject matter that relates to the nature of light itself, quantum or otherwise. And then there's another stream which is about the way in which coherence in matter is induced by light. And we'll talk about what it means about quantum coherence in matter very soon. It's going to be the main subject of our discussion for the earlier part of this course. And that has at its roots, we go back here to, ancient history, ranging from Michelson interferometry onwards, from Stern-Gerlach to laser spectroscopy, laser and microwave manipulations of coherence. All of this was brought together, really, what brought these subject matters together, the optical coherence and the matter coherence, was the development of the laser, now, a long time ago. And so there are aspects of this subject that overlap with what people traditionally call laser physics. And so I know that some of you are optical science engineering students, and we're going to talk about certain aspects of the subject that really have deep overlap with aspects of laser physics. So this is kind of the background under which all of this sits. But I would say what brought me to the subject, I studied this subject as a PhD student because what I was excited about, what I really wanted to understand was the foundations of quantum mechanics itself. And quantum optics has been the forum, has been the arena in which the deepest questions about the nature of quantum mechanics itself have been addressed. Tests of Bell's inequalities and non-locality in quantum mechanics were done first in optics. And it was really the language of the foundation of quantum mechanics that has now become the language that set the stage for the major applications that we currently have in quantum optics in the subject of quantum information science, and the ability to harness the special aspects of quantum systems to enable to do information processing tasks that we couldn't do at all if the world obeyed Newtonian physics. And so it's really the quantum opticians who were kind of there, I like the analogy I like to look at it, we were like Islam at the time of the Dark Ages. We'll let this go. There is a few different attitudes about quantum mechanics. There's the, what the hell does it mean, and the shut up and calculate attitude. And You know, both are important, right? If you just fret about what it all means, you never can actually use it to both be able to understand the nature of the natural world and apply things in important ways. But at the same time, if we don't really know what we're talking about, there's only so far, I feel, one can use it. And quantum opticians were really counterculturalists. In fact, you may have heard about a book called How the Hippies Saved Physics. You ever hear that book? You should read it, it's fun. And it's the story of physicists who were at UC Berkeley, you know, not having jobs after there was a big recession, you know, in the early 70s or late 60s. And, you know, extrasensory perception and other stuff like that was pretty popular with hippies. And the idea, well, maybe in tangled states, you know, you could communicate with extrasensory perception. But anyway, the point of the real story is that the quantum opticians, these hippies, decided they really wanted to put quantum mechanics to the test, and kept alive the discussion that had been put aside pretty much by the 1930s. Everyone had basically decided, look, Einstein said, we got it, we understand what this is, just shut up and calculate. But we didn't fully understand that really yet. And quantum optics has been the form in which we can really think about these questions, and we're going to do that throughout the course of the year. All right. So let's get started, unless anyone has any other questions. By the way, I'm going to be, I should say one last thing about this in terms of office hours. I'll be emailing and maybe setting up a doodle poll so we can figure out the best possible time. I don't think it will be, given the size of the class, to have everyone be available for all hours. But we'll try to do our very best to accommodate everyone so that we can have office hours to be able to have discussions about whatever in the class and homework, etc. Okay? All right. So, as we were just saying a moment ago, quantum optics has been, in some sense, one-to-one with the birth of quantum mechanics itself. Of course, we have 1900, we have Klein explaining black body radiation. So, of course, Max Planck was trying to understand the thermodynamics of light itself, and it just didn't work with classical physics. And the introduction of the quantum of action which we now call Planck's constant, the origin of this has at its heart the electromagnetic field. 1905, Einstein and the quantum of light. This is an interesting story. You know, most of us, when we learn in our modern physics problem, we hear about Einstein explaining the photoelectric effect. And you know, of course, he won the Nobel Prize for that, and that this is what this paper was about. But it's actually fun to read this paper. I'll send it to you. It's not really what Einstein was writing about in that paper. It's true that he ultimately explained the photoelectric effect, but what he was really interested in was this. And the question was, could one understand the Planck law for things like the spectral density of black body radiation by thinking about light itself as a gas of corpuscular quanta. The entropy of a gas, could that explain that? You know, back of course around the beginning of the 20th century, end of the 19th century, the whole question was about the atomistic nature of matter. You know, before that there wasn't really a consensus. The idea that there was an ether, there was a continuum of matter, or the idea that there were discrete fundamental atomistic pieces of things was coming into view at this point in history. But it was pretty settled at that point that light itself was not like that. But Einstein postulated that perhaps we can understand what was going on here by thinking about the fact that light itself was made up of atomistic pieces, just like gases were, which was quite controversial at the time. The idea that there was a kind of fundamental statistical fluctuation relative to the corpuscular nature of matter. Well, now there was a nature of light. Interesting, I was just reading, so, you know, J.J. Thomson, who discovered the electron, which was, you know, one of the first discovered fundamental particles, had a student named Taylor, who, so Thomson was also thinking about the idea that light itself had fundamental components, quanta. Now, and this was motivated by Einstein. And Taylor, who was an undergraduate in 1909, did an experiment looking at the interference of what was called then feeble light, okay? Meaning very, very, very weak intensity. So the idea was to say, suppose one attenuated light so much that there was, in whatever interval, extremely low probability of there being more than one quantum of light in that. Would we see interference in that? And the idea was, no, you wouldn't. That interference somehow was some collective phenomenon of all of this, but this was, because of course I had no idea about quantum mechanics at this point. And what Taylor showed, he was an undergrad, was that no, in fact, no difference in the interference. Now, one might think, I was taught, you know, back in the day, that this was one of the first demonstration of interference by individual photons, and that this was an example of sort of the quantum nature of light itself. But it's actually much more subtle than that. And as we will see, as we'll come to discuss a little bit later in the semester, really, this is really classical light, even though it's attenuated very, very high, and to very, very high extent. This kind of light is still what we would call classical light. And being able to distinguish what we mean by classical versus non-classical light is more than just taxonomy, you know, putting it in which kingdom it is it classical or not. It whether the light should be classified as classical or not has important consequences for the resource that that light has for you to do things, okay? Like process information in a certain way, share a secret or not, okay? So we're going to come back to that. And this distinction of classical versus non-classical light really came into the focus in the 1960s, early 1960s, and the father of modern quantum optics is one of my heroes, Roy Glauber, who just passed away last December. Roy is kind of a friend of our department. He was the PhD advisor of a number of our faculty, including Kevin Gale. And so Dr. Prasad, as many of you know, Professor Prasad recently retired. He was also a student with Roy. And we're going to study later in the semester the Glauber theory of quantum coherence, which is the foundation of modern quantum optics. So, this question about light itself is, as we say, you know, back in, let's go back in time now to 1800 something or other, gosh, 3. It was settled, of course, or so we thought, with Young's double slit experiment. The Young double slit experiment, I mean, before then there was the raging debate, the Newtonians versus, I don't know who the Youngians were. I'm sure they were precursors to the Youngians. Who were they?
Huygens.
Yeah, Huygens, yeah, but I think they were even older. I don't remember where Descartes was in there somewhere. But it's fun. As I get older, I find the development of the history of physics fascinating because, we tend to think as we're students, these things are kind of handed down to us on tablets, with the burning bush, but in fact they're not. They're ideas that were developed by people, and there's history and how those ideas, and those ideas are mutable. They're not immutable, and we should be remembering that we should be challenging ideas. Even though I'm up here presenting them as immutable, they're not. Anyway, of course, the double slit experiment, we take a pinhole, get some light coming in here, we get this wavefront that comes in to these double slits, and then somewhere along the line there's our screen. And what we see on the screen, of course, is intensity fringes. The intensity, as a function of distance along this plane, has these bright and dark fringes, which we understand from a wave perspective in terms of interference. And this was the nail in the coffin of the Newtonian theory of particles of light, because there's no way that you could explain this kind of pattern thinking about particles of light. One must think about waves of light. Now, interference is the cornerstone here. And this brings me to the definition of coherence. What do we mean by coherence when we're talking about interference? So how would anybody define the term coherence? Any thoughts?
frequency?
Sorry?
The frequency of the lights are same.
Something about frequency. So well, we have different kinds of coherence. One talks about, this one might think about this in terms of temporal coherence. Whether a light source is coherent or not, say something about how it's changing in time. We can also think about spatial coherence across some wavefront. Of course, this first pinhole, and as you can see, my drawing skills leave a lot to be desired. But this first pinhole here is placed here in order to create spatial coherence of the wavefront. So there's both temporal and spatial coherence. But coherence, really what we mean by coherence, I would say, in a broad sense, is the capacity for a system to exhibit interference. A system is coherent in this sense if it exhibits interference. So a light field is temporally coherent is if the light at different points in time can interfere with itself. The light is spatially coherent is if different points in space can interfere with themselves. So those examples of coherence. But then we can talk about quantum coherence. And the ability for a quantum system to exhibit interference. I'll come back to that in a moment. Coherence and interference. They are intertwined. So if we're going to talk about coherence as the backbone of quantum optics, then I want to begin by, if we ease our way into the semester, just thinking about very basic, let's think about an interferometer. As the device that will allow us to look at a system, whether it can interfere or not. So, to begin with, let's just talk about classical electromagnetic waves. And so, typically what our system is going to measure, we're going to measure the intensity. I'll loosely say light, but we can talk about any kind of electromagnetic wave, it would be microwave. Okay? Typically, we're talking about light when we're talking about optics. Intensity, well, the intensity we are typically talking about here, if we're talking about light, our detectors won't be able to measure the instantaneous fields. And we'll be thinking about a detector that responds only so fast, it can't respond at attosecond time scales. So typically, our meters will measure the time average of whatever the field is. In this case, the intensity is given by the Poynting vector. Let's think about the magnitude time averaged. Okay? So my Poynting vector here is, and you have to live with me for at least a semester, there will be no mu naughts and epsilon naughts in my class, and you have to learn to speak Sanskrit, also known as Gaussian CGS units. You know, get to be the boss sometimes. All right, so that's the Poynting vector. This is the flux of energy per unit time per unit area. And if we think about our fields as plane waves, we'll write the field at some position in time here as the real part of complex amplitude. So this is the notation I will use. A little tilde here means complex amplitude. Means it has an amplitude and a phase, or a real and imaginary part. And if this is a plane wave here, then we have some polarization. I can write my complex amplitude as having some complex polarization and some complex amplitude here. So E0, if I don't have a vector, I don't put the tilde on top. So I can have shoes and hats, as you know. I like both. So my complex amplitude here has, say, a magnitude and a phase, for example. Okay? And the polarization itself could be complex, right? I could have linear polarization, I could have circular polarization, I can have elliptical polarization. Okay? And my unit vectors will always have an E sub something, so this is the unit vector in the k direction, right? Okay, so what this means then is that the intensity at some position here, for a case of the plane wave, is equal to, well, I can plug those guys in, and that's going to be equal to 1 over, or c over 8 pi, the magnitude of E tilde squared. Okay. So when we talk about this in quantum optics, we often, when we talk about the intensity, we forget about this prefactor and don't write it actually in power units, and we just talk about the intensity as the square of the complex amplitude. Okay. Although, you know, to put it in real units, or you put it, you know, and put in the appropriate epsilon knots in modern language. Okay. So that's how we're going to write the intensity. And so let's talk about an interferometer now. Okay, so firstly, let's just think about what I mean by a 50-50 beam splitter. A 50-50 beam splitter just means something that if I have some input intensity, and I put it on this 50-50 beam splitter, let's say in this port 1, I sub 1 in, there's I sub 1 out, and I sub 2 out. If it's a 50-50 beam splitter, then the output intensity is just 50% of the input intensity in each port. Okay. And this is also true if I put the input intensity in the other port. It can be reflected or transmitted with 50%. Okay? Sometimes called a half-silvered mirror, but we don't use silver anymore. Okay, so let's suppose I have such a beam splitter. I send in light into this port of my interferometer. And now what I'm going to do, I have, as we know, half the intensity comes out here and half the intensity comes out here. Okay. Now let us suppose that I'm going to redirect these beams. I'm going to place a mirror over here and another mirror over here. And redirect these and recombine these two beams on another 50-50 beam split. So now I ask you the following. What intensity comes out of this port and what intensity comes out of that port?
Would be 100% through I1 and 0 through I2.
Exactly. So this is going to be equal to the input intensity, and this is going to be 0. Of course, we understand that as an interference effect, right? That is, there is an electromagnetic wave that splits off. Some fraction of the electromagnetic wave is transmitted. Another fraction of the electromagnetic wave is reflected at this beam splitter. They are recombined at this beam splitter, and the combination of those two fields interfere. And they constructively interfere. Of course, we kind of cheated. I didn't really actually, the answer was indeterminate because I didn't tell you what, I have two paths here, each with a path length LA and LB, and only when LA equals LB is this true. If the paths of the two interferomers are not equal, then it's not necessarily the case. In fact, you can get exactly the opposite. I can get 100% out here and 0 out here, depending upon how I align this interferometer. So now let's remind ourselves how we actually would predict this. Okay. So what I need to do firstly is to think now about not just what happens to the intensity at this 50-50 beam splitter, but I need to think about what happens to the electromagnetic field. In fact, I only care about the electric field because at the end of the day, that's what I'm detecting, and my intensity is related to the square of the electric field amplitude. Anyway, so let's redraw this picture now. And let's say the following. I have this 50 beam splitter. I have some complex amplitude for the electric field in here. And I'm going to allow myself the possibility also of electric field coming into the second port, okay? Because we want to treat this case as well. And then I'm going to have some electric field coming out port 1 and some electric field coming out port 2. So I'm going to write this in a little column vector because there is a linear relationship related by a matrix that relates the input and output fields. That matrix we would call the scattering matrix in quantum mechanics, but it's also true for electromagnetic waves. I could talk about the S matrix. So I want to know what is the linear relationship between them. And there's a 2 by 2 matrix that relates them. Okay. Now, exactly what these matrix elements are depends on how this beam splitter is coded and whether it's symmetric or not. Let's say that it's a symmetric beam splitter, so it doesn't matter whether I'm sending things in from this port or that. It looks the same, it's coded the same on both sides, right? So, what that would say then is that this output field is equal to, well, there's some transmission amplitude times E1 in, and some reflection amplitude for E2 in, right? So T and R, little t and little r, are generally complex numbers because we're working here in terms of complex amplitudes. You know, we're still talking about classical waves anyway, instead of heard about quantum mechanics yet. Nonetheless, we're going to use complex amplitudes to describe that. So that's what we got over here. And then it's symmetric, right? So E2 out is T, E2 in plus R, E1. Very good. So firstly, before I come to the interferometer, let's just take a look at this expression. And let's look at the total intensity that's out, which is the sum of the intensity out of port 1 and the intensity out of port 2. And that's equal to the sums of the squares of the amplitudes for each one of these guys. Right? So that's equal to T squared I1 in plus R squared I2 in plus T R star E1 in E2 in star. Let me make that so let's make sure I get all my factors right. All right, now if this is a lossless beam splitter, so there's no absorption of the light at this beam splitter, then what we want is this to be equal to the input intensity if everything is lossless, which is the sum of the input intensities in the two ports.
TRs.
Thank you very much. Thank you. All right, so what this gives us then, if this is a beam splitter that is lossless, then what we see here is that in order for this to be true, the following conditions must hold. We must have that T squared correct. I have this, I have to add these, I didn't add these correctly, sorry. That was just for one of the input ports, now I have for both. Now it's correct. So in order for this to be true, following conditions must hold. T squared plus R squared must be 1, and R T star plus T R star has to equal 0. What does that imply about this matrix? It had this matrix, thus, our scattering matrix has to be a unitary matrix. It's a 2 by 2 unitary matrix. More than that, this is a determinant 1 unitary matrix. This is a special unitary matrix. This is a matrix in the group we would call SU2. Okay. So the beam splitter does that. In particular, if it's a 50-50 beam splitter, so let's take a look a little. This part is easy. This is just saying something about the total transmitted intensity and the total reflected intensity. This is a little bit trickier. This is saying something about the phase relationship, if this is going to be a good transformation. Let's take a look at those equations. So let us write, we'll call T squared capital T and R squared capital R, so that T is equal to the square root of capital T with some phase factor, and R is the square root of capital R with some phase factor. So now the condition that's written over there, that R times T star is equal to minus R star T. What does that tell me about the phases in this case? Well, we can just write these two things together. So I have e to the I times 2 is minus 1. Doing a couple of steps of algebra in my head. Okay? So what does that tell me about the difference in the phases for the transmission and reflection? It has to be pi over 2, or it's a multiple, right? So I can have this minus this, plus or minus pi over 2 modulo 2 pi. Okay. All right, so for example, for a symmetric 50-50 beam splitter, T equals R equals a half. So I can take, for example, T equals 1 over the square root of 2, and R to be I over the square root of 2. That's a perfectly good transformation like that. Which would mean that my transformation matrix, or scattering matrix, is equal to 1 over root 2, 1 over root 2, I over root 2, I over root 2. Which I can rewrite in a way just for fun. We'll come back to this for those who need a little more practice talking about this, but I'll just write this as 1 over root 2 times the identity matrix, put a little hat to say this matrix, So actually, before I do that, just for everybody, let's write this. All right. This matrix is the identity matrix. What's this matrix?
Swap.
It's a swap. I wouldn't call that the matrix, though.
Quantum mechanics makes.
Yeah, in quantum mechanics, what would we call this? X. If you're a quantum mechanic, you call it X, but if you're a physicist, you call it sigma. Right? So, this is the Pauli matrix, which is going to be our friend, man. Those Pauli matrices, we are going to learn to know them more, love them through and through. So this is the matrix, and this is the cosine of pi over 2, and this is the sine of pi over 2 over 2. Now you say, why the hell are you writing it that way? But I'll tell you why in a moment. 1 over 2. Of course, cosine and sine of pi over 4 are 1 over 2, right? So this matrix you may or may not recognize as the following matrix. Cosine pi over 4 times the identity plus I sine pi over 4 sigma x, which is equal to the following matrix. It's the exponential of I pi over 2 times sigma x over 2. Which is what? What kind of matrix is this in quantum mechanics?
It's a rotation.
It's a rotation matrix. This is a rotation of a spin 1/2 particle. By what angle? Theta over, pi over 4 or pi over 2? Pi over 2. So rotation, that's why, because this, you got the angular momentum's got the half of it. So this is a rotation around the x-axis by the angle over 2. This is going to be important for us. The notion that an interferometer can be thought about in relation to rotations on a sphere. It's going to be a unifying principle we'll come back to a bit later. Okay, little aside here, let's come back. Our 50-50 beam splitter is a pi over 2 rotation. Now the fact that it was x and not y, well, that had to do with the phases. I could have chosen a different set of phases. But a rotation around anything in the xy plane would be a 50-50 beam splitter. Yes, sir?
Is that freedom telling me anything special about my interferometer?
Which freedom?
The fact that I can choose the rotation around x or y or...
Yeah, it tells me that if I, depending on how I coat this beam splitter, well, we had this constraint. This constraint is immutable. That's my favorite word of the lecture. So in order for this to be a lossless beam splitter, we had to have a unitary condition, and that was this condition on the amplitudes here for our symmetrical beam splitter. But I could have a slightly different, I could have a T11, a T12, an R12, and R21 that don't have to be equal, okay? And still have this be a unitary matrix. And that I would get different values for these by having this be coded differently on one side or the other so that it's not a symmetric beam splitter, right? And then I can choose those phases how I like for fun and profit. All right, let's come back to our interferometer. By the way, this kind of interferometer with this kind of arrangements of mirrors is the kind we like to use in quantum optics just for, just for exemplary purposes, because we can clearly see the paths. It's equivalent to, say, a Michelson interferometer, which might be easier to align than a Mach-Zehnder interferometer. We always draw them as Mach-Zehnder interferometers because you can see the paths very easily. It's kind of the hydrogen atom of interferometers. All right, let us now come back to thinking about the output at these two ports of the interferometer. Okay. So I have my complex amplitude for the electric field, port 1. Well, that's going to be the interference. Let's call this, we have path A and path B. And there are two different paths, and so by the principle of superposition, there are two ways I can, the electric field can come out there. So let's write that out. E1 going through path A is what? Well, in path A, first I transmit, then I go around, pick up whatever phase is picked up in the propagation, this distance, and that phase is equal to e to the I k L A. And then, if it comes out here, it is reflected. All right? Actually, let's do it the other way around. Let's look at E2. I think that's be more interesting to see. So that guy is transmitted. Times E in 1. And if it goes, the amount of the wave that goes on this other arm of the interferometer, well, that guy is, oh, I forgot, there's an important point here. It gets reflected at the mirror. And when it gets reflected at the mirror, what happens? I get a pi phase shift, right? It's not going to really matter because they're both going to have the same phase. It doesn't really matter, but we should put it in the letter, right? Okay. At the beam splitter, it's not a pi phase shift. It's the phase shift associated with the reflectance of that beam splitter. So I get a reflection. I get a -1 at the mirror. I get a phase e to the I LB, and then I get another reflectance at that, and I add them together. Okay. So, what do we see? Let us consider the case that we were considering before, where we have a balanced interferometer. And I have a 50-50 beam splitter. That is the way we've drawn it. What is this amplitude out in that case? Zero, right? Because I'm going to get minus, I'm going to factor out that phase, and then I get 1 over root 2 squared plus I over root 2 squared, which is 0. It's important that I here kept all of these factors not as complex amplitudes. They're not the magnitude squares, they're the squares of those complex numbers. And the square of the I was important in order to get me to -1, to get destructive interference. Of course, when these guys are not, when the phases are not exactly equal, as I say, if I have an unbalanced interferometer, again, I'll just bring out this guy. I'm going to bring this guy over to, let's do a little bit of math quickly in our hands, and then I'm going to get the following. Okay, what have I done? What I did is I factored out this common factor. You can check if you multiply it through, you get these phases. And then I have a minus sign over here because of r squared. Right? And I factored this out. And this, of course, is equal to I times the sine of K L A minus L B over 2. You get it? And so, of course, when these are equal, then I get 0. And if this difference was, if this was a half a wavelength, then this would be sine pi over 2, then I would get a bright pole over there. Similarly, if I looked at the output on the one port, this would be proportional to the cosine of that. And the sums of the squares would be 1. All right. Let's now turn our attention to thinking now not about classical waves, but thinking about photons. So now I'm, instead of thinking about, I have my laser here, and instead of thinking about this as just a classical wave, I'm going to think about it as some kind of stream of photons. Now we're going to have to think about how rigorously we get that from the full quantum electrodynamic theory, as opposed to our 330 version of modern physics. But loosely speaking, we can think about that as this random stream of particles coming out as to the medium. Now, if I sent this onto the beam splitter, what's going to happen? Well, what we said is that classically we get half the intensity that is transmitted through this wave, through this beam splitter, and half the intensity is reflected. Okay? But suppose now I put a photon counter on each side of this beam splitter. Okay? And this photon counter will go click if a photon hits it, and this one will go click, photon hits that. Okay? And suppose that I know I've adjusted the intensity of the laser field in such a way that there's extremely unlikely to get any more than one photon. I mean, I have the highest probability of getting nothing, and there's a tiny, tiny probability of getting one in the time window in which my detector goes click. So the probability of getting 2 in any of those windows is negligible. Okay. And now I'm going to wire this up into a coincidence counter where this box goes click only if both of these detectors go click within that time window. That's what we call a coincidence counter. What will I see on this coincidence counter?
Be 0.
I'll see nothing if I set it up right, because the photon is one photon. It's indivisible. One photon under Einstein with electromagnetics for all. It either will go click here, or it will go click here, but never go click in both at the same time, because it is a quantum of light. It's an indivisible particle. That's what makes it a quantum. Whereas the electromagnetic wave, half of the intensity went here, and half the intensity went there. But as far as the photon is concerned, you only see a click on one side or the other. Now, what happens when I send this kind of the photon through my Mach-Zehnder interferometer? We just said the photon either goes here or here, in the sense that if I put a detector here or here, I would never see it in both places. I would either get one click or the other. And if it went in one place or the other, if it went in here, we know when it gets to this beam splitter, it should either come out here or here. And this guy, similarly, if it had gone through this port of the interferometer and gets to the beam splitter, it should go either here or here. So when I put my detectors here and I ask about their clicking, I'm not asking about coincidence now, I'm asking does this guy go click or does that guy go click? What's the chance that this guy goes click if this is aligned so that these guys are equal? 1. So even though the photon is indivisible and we never see it in both ports at the same time, there is still interference. And what Dirac famously said in his masterpiece is that each photon only interferes with itself. No two photons interfere with each other. Each photon, one by one, there is now a probability amplitude for going through port A and a probability amplitude for going on path B, and it is those probability amplitudes that describe the probability of detection of each photon that is interfered. These probability amplitudes are in some sense related to our complex friend, the complex amplitude of the electric field. We can think about, loosely speaking, we'll think about how we fine-tune that a bit. This complex amplitude as being something like the probability amplitude of the photon. It's what we call first quantization. But I want to quickly conclude in my usual grace period of 2 minutes over lecture. This question, is this really true? So I'm going to leave you with the following thought experiment we'll pick up again next lecture. So let's think about a slightly different experiment. Instead of taking this, I'm going to take this laser. It's going to be an ultraviolet laser. And I'm going to use it, put it through a crystal, a magic crystal, called the Chi-2 crystal. This is what we call a nonlinear crystal. And what this crystal does is it spontaneously can cause these big, fat, energetic mother photons with a UV of energy into baby daughter photons that have infrared photons. So this is my pump photon, as we call it. And I'm going to have 2 photons. Let's say that I'm going to call them, as we often do, the signal and the either. They're 2 photons such that the energy in the mother photon is equal to the total energy in her twins. These are called twin photons. Okay. So I spontaneously get this 1 photon every once in a while will split into these 2 daughter photons. They're twins. Now what I'm going to do is the following. I'm going to bounce 1 twin off of 1 mirror. It comes out in a particular direction. We'll study this next semester in detail. And then it bounces, I'm going to bounce it back and put it on a 50-50 beam splitter. That is of the same flavor that we just described. Okay? It's the same kind of, has the same transformation. Okay? Okay. So now I can get 4 different processes. I could get what we call reflection. So this photon gets reflected. I can get transmitted, where both photons get transmitted through the beam splitter. I can get reflected, transmitted, or I can get transmitted, reflected. Okay. So these are 4 processes that can occur. Okay. So what I'm going to do now is I'm going to put these 2 detectors and a coincidence counter, just like we had before. But now, with 2 photons rather than 1 photon per time going through, I have these pairs of photons. And these 2 photons now, these are 2 separate photons. It's not 1 photon that is either in this. They're 2 photons. And these 2 photons come together, they're bounced, and they meet each other. The question I have for you is, do I see coincidence? And if so, with what fraction? Think about that for next lecture, and we'll pick it up there. All right? Very good. You will be receiving some email from me asking about office hours, and making sure you have the link to the website and addressing any other questions you might have. So, have a good afternoon, everybody.